quadratic functions. So before I tell you about quadratic functions, let me explain briefly what we mean by a parabola. And so a parabola is the locus of all points equidistant from a fixed point called the focus and a fixed line called the directrix. So if you take any point on the parabola, then the distance from the focus to that point and from this point to the directrix, that these distances will be the same. So the distance from a point to the focus will be the same as the distance from this point to the vertex, to the directrix, and that will be true for any point on the parabola. So a point called the focus and the directrix, a line, will uniquely determine a parabola. Passing through the focus perpendicular to the directrix, I will call that line the axis of the intersection between the axis of symmetry and the parabola will be called the vertex. So let me give you the standard form for the equation of a parabola with vertex hk. The standard form for the equation of a parabola with vertex hk is y minus k equaling a times the quantity x minus h quantity squared. Okay, and that gives you a parabola looking like this, or going down. So if a is greater than 0, the parabola actually goes up. If a is less than 0, the parabola will actually go down. Okay. If a in absolute value is greater than 1, then it is thinner than the graph of y equal x squared. A stretching of the y-axis for the graph of y equal x squared. So we'll just be taking y equal x squared, but just sort of stretching it to make, whereas if a in absolute value is between 0 and 1, it will be fatter than the graph of y equal x squared. I'll be compressing the x-axis for the graph of y equal x squared. So if you had the graph of y equal x squared, so it would look fatter than the graph of y equal x squared. Now, if instead I have, then this is also called the standard form for the equation of a parabola, x minus h equals a quantity y minus k quantity squared, then this also is a graph of parabola, but instead of going up, down, it'll go right, left. So it'll either look like this or like this. So instead of going up, down, like this guy, it goes right, left, like this. And so if a is greater than 0, it opens up to the right. If a is less than 0, it will open up to the left. If A in absolute value is greater than 1, just like in the previous case, it'll be a thin parabola. It will be thinner than the graph of y equal x squared. If A in absolute value is between 0 and 1, it'll be fat. It will be fatter than the graph of y equal x squared. The general form for the equation of a parabola is y equals ax squared plus bx plus c. Of course, you could also have it, if you have the parabola, this would be for a parabola that goes up, down. If instead you had x equaling, purple, I want black, x equaling a y squared plus by plus c. This would be also the equation of a parabola, but instead of going up, down, the right, left. The axis symmetry is just x equal negative b over 2a. The vertex will have coordinates. Well, the x coordinate will be minus b, the equation here of the axis symmetry. And the y value is, well, whatever the y value is by plugging in the x value. Okay. Of course, if it's in this form, the axis symmetry would be y equals minus b over 2a. Just like before, if a is greater than 0, it goes up. If a is less than 0, it goes down. If a in absolute value is greater than 1, it's thinner than the graph of y equal x squared. And if a in absolute value is between 0 and 1, it's fatter than the graph of y equal x squared. And well, if it goes right and left, it still has the same properties here. Okay, on page 305, let's do problem number 14. Determine whether the graph of each quadratic function opens upward or downward. State whether a maximum or minimum point occurs at the vertex of the parabola. So in this case, all you want to do in these problems is determine, does this parabola go up or down? So if you remember, it'll go up or down depending on the sign of this quadratic coefficient. And so I look at the quadratic coefficient. In this case, a is 2. Since 2 is greater than 0, this means that the parabola points upward. Next, if the parabola points upward, then it has a minimum point, and that minimum point occurs at the vertex. And so it has a minimum at the vertex. And that is your answer. So it goes upward, and at the vertex, that vertex will be a minimum. Problem number 20. Find the vertex of each parabola. Okay, so first off, let me rewrite f of x as y. So y is equal to 1/3 x plus 1 squared minus 5. Let's add 5 to both sides of my equation. So y plus 5 equals 1/3 x plus 1 squared. Okay, so let's try to find the vertex, so it's in standard form. And so just recall that in standard form, y minus k equaling a x minus h squared, the vertex is hk. So therefore, the vertex here is just, well, whatever I'm subtracting from x, well, this is a plus 1, so therefore the vertex is minus 1. And whatever I'm subtracting from y, well, again, it's a plus 5, so this will be a minus 5. So my vertex is at the point -1, -5. Let me do problem number 24. So y is equal to x squared minus 10x plus 25. So I wanted to determine my vertex. The axis of symmetry is, well, x equal -b over 2a. And this is for equations in standard form, in general form, quadratics in general form, y equaling ax squared plus bx plus c. And so let's determine my axis symmetry. So it's x equal -b, the number in front of x, -10, over 2a, the number in front of x squared, 1. And so negative times negative is positive. 10 divided by 2 is 5. So x is equal to 5. So that is the equation of my axis of symmetry. This will give me the x coordinate of my vertex. So now let's determine my y coordinate. So this is the x coordinate of the vertex. So now let's find the y coordinate. To find the y coordinate for my vertex, I'll just plug in for x, 5, into my original equation, and solve for y. So y is equal to 25 minus 50 plus 25. Well, 25 minus 50 is -25, plus 25 is 0. Therefore, my vertex has coordinates 5, 0. Oh, and of course you denote the vertex by V. Let me do problem number 57. Let me just move this up a little bit. Okay. Let me get another page. Okay, so let me do problem number 57. Maximizing storage area. A farmer wants to partition a rectangular feed storage area in a corner of his barn. as shown in the illustration. Let's see if I can show the illustration. Oh, that gives, so let's show the illustration. Okay, there. So a farmer wants a partition, a rectangle, there it is. There, okay, voila. And so he has this partition. So he's partitioning off this storage area. So I have this storage area. I can read the question here. So a farmer wants to partition a rectangular feed storage area in the corner of his barn, as shown in the illustration. The barn walls, so these barn walls, form two sides of the stall. The farmer has a total of 50 feet of partition for the two remaining sides. What dimensions will maximize the area? So he can either make it like a really thin, long, partition, or he can make it making it much wider. And the question is, well, what configuration will he do so he maximizes this area here? Okay, so let's do that. Trying to get back. 3.2. Okay. So basically he has these walls. Maybe I'll do it a little. So he's got, there. So he has, this is my partition. And maybe I'll call this X. Oops. Oh, well, actually, maybe I'll keep it in red. And this is Y. Okay. And these are feet. Okay. And then on the other side, these are the existing walls, which I don't really care about. I just care about the partition. So I have 50 feet of partition. Okay. So I want to maximize the area. Well, the area of a rectangle, oh, maybe I should, well, this is a rectangle. The area of a rectangle is just length times width, so xy. Where, so we're subject to some constraint. This is called the objective equation. This will be called the constraint equation. That, well, we have a total of 50 feet of partition. So we're constrained to the fact that the length of the partition, x plus y, is equal to 50. Okay, so now let me solve y in terms of x. So let's subtract x from both sides of my equation. And now let's replace y here in my objective equation by the solve for variable. And so this is equal to x times 50 minus x. Let me multiply the x inside the parentheses. And so I get that a is equal to, let me write the negative x squared first, plus 50x. So now I notice that this is quadratic in A. So this really is in standard form, the standard form of a parabola. General form. Why did I write standard? Sorry about that. The general form for a parabola. Y equal ax squared plus b plus c. Okay. Here, of course, instead of calling it y, I called it a. In a was -1, b was 50, and c is 0. Now, we want to maximize this. Well, a is equal to, is greater, if a is less than 1, well, so I guess I'll just say in this case, a is -1. And -1 is less than 0. But if a is less than 0, that means that this parabola points downward. If I have a parabola pointing downward, then at the vertex, we're at a maximum. So then I have that the maximum occurs at the vertex. So to maximize this, I just have to determine, well, what is the vertex? Well, to find the vertex, I just have to look at the axis of symmetry. That will give me the x-coordinate of the vertex. And so the x-coordinate of the vertex will be, well, determined by determining the axis of symmetry, which is x equals -b over 2a. So let's do that. So I have x equals negative, well, b in this case was 50 over 2a. A in this case is -1. And so negative times negative is positive. The negatives cancel. 50 divided by 2 is 25. So x is 25. So that means that the maximum occurs when x is 25. Well, good. That tells me what one of the sides is. Let's figure out the other side. And so y equals x minus 25. That's what we saw for y at the beginning here. 50 minus x. Did I say, yeah, well, 50 minus x. It's 50 minus x. And so y is equal to 50 minus 25, which is 25. Therefore, the maximum occurs when x is 5 and when y is 25. What are the dimensions? So the dimensions are 25 feet by 25 feet. That will be the dimensions for which this partition maximizes the area. Okay, let me do problem number 59. Actually, get one more line up there. So problem 59. Sheet metal fabrication. A 24-inch wide sheet of metal is to be bent into a rectangular trough with the cross-section shown in the illustration. So here's the illustration. Find the dimensions here that will maximize the amount of water the trough can hold. That is, find the dimensions that will maximize the cross-sectional area. See if it takes a second to come up. Well, it says it's coming up. It's up there. There it is. Okay, so here it is, right here. So I have this a 24-inch wide metal sheet. So this is some metal sheet is bent. So I bent it here into a rectangular trough with cross-sectional area. So this is my cross-sectional area here. I want to maximize the amount of water. In order to maximize the amount of water, I want to maximize the volume of this. Well, the length is fixed. And so to maximize the volume of this, I just want, so that is, find the dimensions that will maximize this cross-sectional area. So I just want to maximize this cross-sectional area. Okay, so let's do that. So I have this water trough. And somehow I want to maximize, maybe there. Actually, that's, okay, so I want to maximize this. Okay, so let's call this y, and let's call this height here x. Okay, I wonder why that came up. And so let me get some more room here. So, oops, that's x doesn't look good. This is x. Actually, this thing here is x. Maybe I'll put the x here. So this is x, and this is y. So I want to maximize this cross-sectional. Oops, of course I wrote it the wrong way. That this is y here, and this is x. So I want to maximize this area. Okay. So I want to maximize. I'll call it A. And I had that the total length here was 24 of the sheet metal. And so subject to the fact that if I take this total length here, x plus y plus x, so 2x plus y, I must get that it is 24. Just like before, let's solve this equation for y. So let's subtract 2x from both sides. And now let me replace y by 24 minus 2x. Let me multiply x inside the parentheses. So I get a 24x minus 2x squared. Let's write the negative 2x squared first. And just like before, well, this is, if I look, this is a the general form for the equation of a parabola. And so let me determine if I want to, so in this is negative 2, which is less than 0, which means that I will maximize. So it means it's pointing down. Oops. I gave more than one. So let's insert. Okay, there it is. So it means that since a here, the coefficient in front of the quadratic term, is less than 0, it means that this points down. This is downward. Since the parabola points downward, this means that we have a maximum, and it occurs at the vertex. Good, just like before. And so we can determine the x-coordinate of this that maximizes this area by looking at the x-coordinate of the maximum can be determined by just looking at the axis of symmetry. X equal negative b over 2a. So in this case, b is 24 and a is negative 2. Negative divided by negative is positive. So you should get 24 over 4. Okay, let's get another page here. And so 24 divided by 4 is 6. So that gives me the x-coordinate of the, gives me the x-coordinate of the vertex. So to find the y-coordinate of the vertex, well, let's just substitute in for what y is. So I know that y, so since y is equal to 24 minus 2x, then I have that y is equal to 24 minus 2 times 6. This will be the y-coordinate that maximizes the area, that maximizes the flow through this trough. So y is equal to 24 minus 12, so y equals 12. And let me just see, what were they asking? I forgot the exact Find the dimensions. So let's find the dimensions. So this will be maximal. Let's find the dimensions. So the dimensions will be 6 inches by 12 inches. That will be the dimension of the trough that will maximize the flow. So it's a 6 by 12, and then on the other side, another 6 inches. Okay, so let me do problem number 82. Let me move it up one more. I'll see the illustration, okay. Oh, can I do that really quick before you see anything? Okay, so see if I can do this. Problem number 82. No, 82 doesn't do that. I want to say changes. No. Just get rid of that. Oh, let's just see. Okay, can I stop this for a second? Okay, good. So stop that for 1 second. Hopefully. Okay, so now let's see if I can get this back. Okay. Oops. It'll take me a second here, sorry. Just so I can show you the illustration. Hopefully you're not seeing this, but okay. Okay, so see if it comes back up. Okay, now I'll try to get back. Oh, why is this taking so long? Okay, share screen again. So let's share screen again. Okay. Okay, so, well, that's, okay, 1 second. Okay, well, forget this. Okay, so, it's not showing me this. Okay, we were in 3-2. Okay, so, I'm not able to show you that for some reason. The point P lies in the first quadrant and on this line. Okay, so point P lies in the first quadrant. And on the line, x plus y equals 1. Okay. So suppose this is 1, and this is 1, x, y. So the point P lies in the first quadrant, and on this line, so let's say that this is the point P. In a position such that the area of the triangle, this has got to be O. Oh, and this has probably got to be A here, such that this triangle here, that the area of this triangle, let me actually put this in red or something, so that the area of this triangle is maximal. Okay, so I want that this area here is maximal. Okay, so I want to maximize that. Well, I have that the area of a triangle is 1/2 base times height. Okay, good. So all I want to do is figure out the base and height of this. Okay, so let me redo this again. So this is X and Y. So this is going to be X, and this will be Y. Because we're in the first quadrant, and this has coordinates X, Y. So if we're in the first quadrant, then the coordinates X, Y correspond to these lengths here. Okay, good. So I want to maximize the area (1/2) base times height, subject to, well, the constraint that this point is on the line. Well, the line has the equation x plus y equals 1. Okay, so just like before, let me solve this equation for y. So subtracting x from both sides of my equation, I have y equal 1 minus x. And so let's substitute for x, for y, 1 minus x. So let's multiply the 1/2 x inside the parentheses. So I have a equals 1/2 x minus 1/2 x squared. And let's write in descending order. Negative 1/2 x squared plus 1/2 x. This is written in general form of a parabola. And so a in this case is negative 1/2, which is less than 0, which means that this has a maximum at the vertex. And so the x coordinate of this maximum of the vertex will be determined by the axis symmetry. Which has the equation x equal negative b over 2a. And so x is equal to negative. B in this case is negative 1/2. A in this case is positive. No, I'm sorry. B is positive 1/2. Sorry. A in this case is negative 1/2. Negative divided by negative is positive. 2 times 1/2 is just 1. 1/2 divided by 1 is just 1/2. So x is equal to 1/2. So that is the x coordinate. That gives us the maximum. Now let's determine what y is. Well, to determine y, I know that y is equal to 1 minus x. Then, oh my goodness. Y, okay, why is this frozen for a second? Y equals 1 minus 1/2 plus 1/2. Therefore, the coordinates of my maximum are at 1/2, 1/2. And that is your answer. Okay, so that finishes off